Hi everyone, my name is Zhiqiang He. I am a first-year PhD student at the University of Science and Technology of China. My talk today is about a new RDMA network virtualization solution for VPC. This is joint work with researchers at Huawei and Professor Zhili Zhang from the University of Minnesota. In the public cloud, VPC is used to let users define a virtual network for their virtual machines. Nowadays, VPC demands a high-performance virtual network because more and more network performance-sensitive applications are deployed into it. At the same time, RDMA is currently an important technology for building high-performance networking in the data center. For now, the RDMA network can provide about 200 gigabits per second or higher throughput and 2 microsecond round-trip latency on the one switch. So bring RDMA into VPC is worthy work. For the traditional TCP/IP network, VPC uses the packet-based network virtualization to provide virtual networks. It introduced a software-based virtual switch in each host to realize the virtualization logic. Suppose virtual machine A wants to send some data to virtual machine D. The virtual switch will encapsulate machine A's each packet with the host IP address, so that the packets can be routed on the host network and finally delivered to the virtual machine D. However, packet-based virtualization cannot be directly applied to the RDMA network. Compared to the traditional TCP/IP network, RDMA offloads the network stack to the hardware called ARNIC. Data sent from the application are directly DMA'd to the ARNIC, and the packets are encapsulated on the ARNIC. We can see that RDMA bypasses the host software and thereby the virtual switch. So we cannot directly use a virtual switch to realize network virtualization for RDMA. So where and how to realize RDMA network virtualization and other features required by the VPC. Based on our observation about RDMA communication, a context called QPC is the key for the ARNIC to process the network packets. For example, after reading the application's data through DMA, the RDMA will use the destination IP in the QPC to encapsulate the network packets. So our basic idea is that we can virtualize the RDMA network by controlling the QPCs. And since all the QPCs are maintained on the RDMA driver, we can perform QPC controlling in pure software. Following the basic idea, we propose MasQ for RDMA network virtualization. Now we give MasQ's architecture. To control all the QPCs, MasQ introduced software on the host. Then any requests potentially operating the QPCs will first be forwarded to the MasQ software, and then to the ARNIC for further processing if needed. For requests only referring the QPCs for data transmission, MasQ just leave them untouched. Since these requests still bypass host software, RDMA's good communication performance still hold. However, to build a well-functional RDMA for VPC, we have 3 challenges to solve. First is how to provide a standard ROCE device in a virtual machine. This is important for supporting the applications who access the RDMA network using an IP address. Second and third is how to realize network virtualization and the application of security rules in MasQ software. These 2 are the basic features required by the VPC. In the following, we give a see at MasQ's key mechanism to solve these challenges, and the design details can refer to our paper. First is how does MasQ provide a standard ROCE device in a virtual machine? A standard ROCE device consists of 2 interfaces, including an Ethernet interface and an RDMA interface. For best capability, the 2 interfaces should be both appeared in the virtual machine. To this end, MasQ used the generic Ethernet interface virtualization method to provide a virtual Ethernet interface and use the hybrid I/O virtualization method to provide a virtual RDMA interface. The problem is that the 2 interfaces are separated. So VBond is proposed to bind the 2 interfaces to provide a ROCE device, so that the application can access the RDMA network using an IP address. We now give a see at MasQ's design on network virtualization. The core idea is to replace the virtual IP address in the QPC to the host IP address. First, the QP setup request issued by the application is forwarded to the MasQ software. Then the MasQ software replaces the virtual destination IP address with the host destination IP address and writes it into the QPC. After the QPC is cached, data sent from the application will be encapsulated with the host IP by the RDMA stack. Then the packets will be injected to the host network and finally routed to the target virtual machine. To this point, network virtualization is achieved. The MasQ software also supports the application of security rules. By rejecting the request or changing the QP's state to error, it can prevent any bad guy from injecting its traffic into the network. Now for the evaluation. In this part, we want to show that whether MasQ can provide competitive performance. We compare our solution with 3 other RDMA networking. Host RDMA and SRIOV are involved as the baseline. FreeFlow is the newest software-based solution for RDMA network virtualization. All candidates are evaluated in the same test bed, consisting of 2 servers directly connected by Rokinix. Each server is equipped with 2 powerful Intel CPUs and a big enough memory. We run virtual machines using Camel and also run containers for FreeFlow using Docker, because FreeFlow's prototype can only support containers. We first use perf test to measure the average latency for sending or writing a 2-byte message. The result shows that MasQ can achieve the same latency as SRIOV. MasQ's latency is a little worse than host RDMA because MasQ's default mode will use the RNIC virtual function to enforce queues. We find that the RDMA performance over virtual function is worse than that over the physical function. So if queues is not needed, MasQ can directly map the QPs to the RNIC physical function. The experiment result shows that MasQ can achieve almost the same latency as host RDMA by using the RNIC physical function. We also use perf test to measure the throughput with different message sizes. The results show that MasQ can achieve the same throughput as host RDMA for all message sizes. For messages less than 8 kilobytes, MasQ performs better than FreeFlow. We also choose 3 typical application benchmarks to test MasQ's performance. We include the Graph 500 benchmark for the HPC scenario and the key value stone benchmark for the web system scenario, and the Spark RDMA for the big data scenario. The results show that MasQ performs well in all applications. And in the key value stone benchmark, MasQ achieves 10 times better throughput than FreeFlow. Finally, does MasQ introduce any overhead? MasQ takes a slightly longer time in the QP setup stage. In our test case, the overhead is about 11% longer compared to SRIOV. And for most applications, the QP setup stage is not on the critical section of the application's overall performance. So actually, the overhead can be negligible. Now for the conclusion. We conclude by summarizing the contributions of this work. MasQ first proposed to virtualize the RDMA network in the QP setup stage, and it further proposed 3 practical mechanisms to realize features required by the VPC. A prototype of MasQ is implemented and evaluated against the big data and HPC applications. The results show that MasQ can achieve almost the same RDMA performance as host RDMA. Here are some future work worth to explore. First, the containers are also widely used in public clouds, so we can use MasQ's method to bring RDMA into containers. Second, virtual machine live migration is a very important feature in VPC, so enable live migration for the RDMA-capable virtual machine is also a worth future work. Thank you for listening. Questions are welcome.
All right, thank you, Ji-Heng. While the questions are coming in, let me kick off the discussion with maybe a little bit of a high-level question about Rocky. As you know, Rocky has issues in terms of it relies on PFC and pulse frames. And so I just want to hear your thoughts on, do you think largely Rocky can be virtualized without causing big performance coupling between tenants? What do you think are the challenges with relying on Rocky?
You mean the PFC problems, punishment?
Pulse frames, yes.
Well, PFC problem is really a big challenge for RDMA, but we think it should be addressed by the congestion control algorithms. Mm-hmm. Well, recently some new algorithms such as HPCC has been proposed. Mm-hmm. According to their statements, the PFC problem has been avoided, has been largely avoided. So since MasQ is orthogonal to them, any advanced congestion control algorithm could be used, and all MasQ's good features still hold.
Mm-hmm, mm-hmm. Thank you. Okay, let me read a question from Tao asking, is there any persistent CPU overhead in MasQ except those in QPair setup?
Well, the answer is yes. Well, we should first there are some communication overhead between the front end and the back end driver communication. Well, like VirtIO based based command forwarding overhead. Mm-hmm. Well, we also have some overhead about the address translation and the reverse validation.
Mm-hmm. Okay. Waiting for other questions to come in, let me jump in and ask another question. What I want to understand how you can provide prioritization across traffic. For instance, if I'm the infrastructure provider, I would like to prioritize my traffic over my tenant's traffic. Is something like that possible with MasQ?
Well, actually, we can use the function provided by the. Actually, the key problem is here is to how to distinguish traffic of the MasQ from other infrastructures traffic, right?
Right.
Where we can use the technology like DSPF to tag our traffic, to tag MasQ's traffic, so that we can distinguish it from other traffic.
Got it. Okay. Okay. Another question from the audience. Shooting is asking, can you provide more insight on the overhead of free flow compared to MasQ?
Oh, okay. So both MasQ and the free flow are software-based virtualization. Well, the key difference is that free flow forwards all the data path operations to the to the software-based backend, while MasQ just leave them untouched. So, from this perspective, we can see that for small messages, performance of free flow RDMA is worse than MasQ.
I see. Okay. One last question from Anna. She's asking, verbs operations can fail because the QPair no longer work for any operation. How does MasQ resolve this situation?
Well, let me see.
Do you think that's a fair characterization?
I think the problem I think the application should be responsible for this kind of failure.
Mhm.
Well, MasQ does not touch this kind of failure or help them to recover from the failure.
The comment is that it puts the queue pair into an error. Well, yeah, I think Anna, it's better to follow up online. But if I understand, the answer is the application can take care of these queue pair failures independently.
Yeah.
Cool. Thanks so much for your talk. Well, we have a first question, and on Slack from Wei, that is asking whether the fact that you have a limited number of queue pair on the NIC may somehow affect the way in which you set up MasQ. In particular, is asking, does MasQ limit the number of queue pair for each tenant? And in general, are there other critical resources on the RDMA NIC that MasQ is taking care once you want to virtualize across many tenants?
Okay. Well, this is very, very good question. Since all the QP creating are controlled by our MasQ, so we can limit the number of QPs a virtual machine created. However, the maximum number of QPs is cached in the RNIC, and the caching strategies remains unchanged in MasQ, and it depends on the specific RNIC. Well, about the scalability issue, well, as shown in many works, RDMA itself has the scalability issue, and its performance drops when the created QP exceed the maximum number the RNIC can cache. Well, MasQ neither solve this problem nor makes it worse, but we can limit the number of QPs a virtual machine created to tackle or avoid this issue.
Okay. Another question that I wanted to ask is, compared to the traditional virtualization, where you also bring the IP address of the virtual machine, so the 192 and so on, here it seems that when you send packet over the network, you're losing this information because you're only attaching the IP address of the host. Does this create any problem in terms of the network management? Because effectively you're losing the ability, the flexibility over the network to do some packet inspection and potentially, apply some more sophisticated policies.
Well, you mean okay. Could you repeat your question and slow down the?
Yes. So in the traditional virtualization, what you do is that you also include the IP address of the VM. So in the example you were given at the beginning, TCP/IP, where you also are including both the address of the host as well as the address of the VM, the 192.0.0.1. While here you're only attaching the address of the host. Does this create any issue in terms of you can limit the flexibility you can do in your virtualization management?
Oh, okay. Well, actually, MasQ does not carry the the information of the virtual network in each packet. Yeah, but well, for some it depends to support some features. Well, if the switches in the network have a global view of the network, then it can fetch the virtual networks the information from MasQ's controller. Yeah, we have a centralized controller to maintain all the information there.
Okay.
However, if the switches in the network works in standalone mode, MasQ is not compatible with this kind of situation. However, we can enforce the policies in the end host server, and we can support the basic features like security rules and rate limiting queues.
Okay.
Actually.
Okay.